thank you all for coming. And everyone who's gone by the registration desk should have a copy of the program. You might want to look at it in case you didn't see a program of the most recent version. It's been changed and updated in certain respects. This is the second annual conference of the Rotman Institute, and it's an incredible lineup of speakers that we have for this conference. We're very proud of it. The impetus to have this conference on climate modeling and more generally climate science and the epistemology and history of climate science came from a brilliant idea of my colleague Chris Smink, which was to invite several distinguished people working on climate science, a couple of philosophers and a scientist, to come visit us this fall, which eventually has come to fruition. And those people are here today. Wendy Parker is one of them, Lenny Smith from LSE, Wendy's from Durham now, and the other person is Roman Frege. Roman, are you here? There you are. And so we have enjoyed Roman's visit, and recently Lenny and Wendy have arrived, and we're extremely happy to have them here. One of the main ideas behind the Rotman Institute is to get philosophers engaged with scientists on issues that are of real importance, not just ivory tower conceptual issues, although we like those too, but issues that can have some kind of impact. And we feel that climate science is definitely one of those areas in which the interaction of philosophers and scientists may be useful and fruitful. And so that gave rise to the idea for this conference, and we'll see how it works out. I want to briefly thank the people who've made this conference possible, because usually the acknowledgments at the end reach a smaller audience, and I want everybody right from the beginning to know why this is possible, how it's come about. And so I guess first I'll mention our financial benefactors, which are principally the Canadian government by a Shirk grant, which Eric Desjardins was in charge of putting together and was successful, and that was wonderful. And then Mr. Rotman and the Rotman Family Foundation, which provides generous support for the Rotman Institute, and Western University, which has also been very generous in supporting the Rotman Institute. So basically, those three entities have contributed to making this conference possible, and we're very grateful for that. I've mentioned Eric has played a crucial role in the organization of this conference. Eric Desjardins, who's a philosopher of environment and sustainability and related topics here at Western. Martin Wieser, a student working on climate models and related issues, has done an incredible amount of work for this. And a number of other people who you'll see around and meet have contributed a lot to making this possible. All right, so without any more preliminaries, I'd like to introduce Jim Fleming, our first speaker. He's from Colby College, and he's going to give us a really interesting talk about shape-shifting nouns.
Thank you very much. I assume that's applauses for the benefactors, and I'm happy to be here. I'm very delighted to be with your group. I'm happy that they put the idea of historical, scientific, and philosophical perspectives in the conference title, because it's really my role to provide some historical grounding for some of the discussions, and I hope it's valuable to you. I'm interested in shape-shifting nouns. That's sort of my topic is based on the historical assumption that anything you can name is different meanings in different eras. So when you're doing your epistemology of the present, you have to think about what are these objects that you're discussing, and what is the history behind some of that, and how has it changed. So I'm going to have three key terms that come out in this talk, which are some perspectives on the history of the idea of climate, which is very, very, very old, very, very long history, but also the idea of dynamics, which I kind of bring to bear from 1900 or so when Wilhelm Bjerknes brought in his circulation theorem and the idea of a dynamic climatology. And then models, which again is an ancient idea. We'll allude to Democritus, but we have to think about what we're thinking about when we're talking about models. So I hope, I am a historian of science and technology. I have current interests in public policy. and I'm very happy to try to provide some historical perspectives for you. Based some of my remarks on two books I wrote not too recently, but Meteorology in America is a 19th century book about networks and systems and theorists coming up to 1870, before there was a National Weather Service, before there was even a discipline of meteorology. I'll draw a few things from that. And then the Historical Perspectives book on climate change, which pretty much covers the Enlightenment through early modern and then up to recent times. But I always drop the story off, at least my habit had been to drop the story off before the current era, and to try to provide historical grounding for current discussions. I went a little bit beyond that in a book I wrote called Fixing the Sky, where I got involved in climate intervention and moved the history into conversation with contemporary scientists and policymakers. And then the rest of the remarks are based on this new work I have. It's not published yet, but it's in press, and it's called Everything Atmospheric Everywhere Always, kind of a modest title. But it's a quote from 1960 in which, how I would explain it, the history of atmospheric research in the 60 years of the 20th century, covered in this book, is really an aggressive, I would call it a Laplacian program, to measure everything with the new technologies available, to then try to predict everything out into the future with the laws of physics. And this was the atmospheric program for these 60 years. And it was largely driven by a vision that the laws of physics were becoming known, and they were including thermodynamics and dynamics, and that the measurements were just getting more and more at altitude and more global through technologies that began in 1900 with Marconi wireless and led through the electromagnetic century up to, and through aerospace from the Wright Flyer up through the century to things like Tyros weather satellite. The everything atmospheric quote came from some of the Tyros scientists, but it actually refers back to the whole spirit of the era, in which new technologies were driving the agenda to make a perfectly rational set of measurements that would be, again, able to be used for prediction of future states. So they're basically building a meteorological time machine and seeing how far they can run the clock forward. The brick wall I'll explain later. I wanted to frame Magritte panoptic view a little bit with this brick wall that they ran into. They were warned about the wall in 1900 by Henri Poincaré, but they were also hit the wall in 1960 through the warning of the work of Ed Lorenz. So that's kind of where we're going here.
Would it be possible to turn down the light in the front row?
No, I don't know where the switch is.
Your picture is wonderfully creepy,
Well, Magritte's painting is called The False Mirror, and it's meant to invoke at least this everything atmospheric panopticism. And then I added the Photoshop brick wall around it. We'll see if it actually becomes the cover of the book. It's in press now. So I spent pretty much a sabbatical year working on a metaphor, which was apprehension, and I applied this to climate history. The first meaning of apprehension in the Oxford English Dictionary would be awareness, understanding, coming to not necessarily completely understand something, but becoming aware that something's happening. And when our object of cognition is the climate system, we can clearly say that nobody has the high ground on that. We live in a changing climate, all different time scales. It's very hard to point to it. An astronomer might point out a supernova, observe it in a telescope, but the climate system needs to have some other ways of apprehension. We in actuality grasp nothing for certain. That's a statement from Democritus. And it was very hard to get a grasp on the climate system. So building up ways of knowing, or authoritative ways of making statements about the climate, was an important thing for me. And I had collected, really literally, as they say in the younger generation, tons of material on this, but I was having a sorting problem. And when I found my metaphor, I was able to sort part of my documents into awareness documents, another part into anticipation and dread kind of documents where people were fearful of the return of the glaciers or the volcanic weather or things that might damage their food supply. Generally, that's again just from the OED, that fears and apprehensions of such things. And then the third one was intervention and control. Again, the three major meanings of the word apprehension, which would be getting apprehended on the freeway if you're going too fast, you're stopping something. And so this idea of a warrant for your apprehension, this led later on. I wrote a little bit about this in the climate book, but this led later on to another book on fixing the sky that I worked on recently. I think I mentioned it already too. So using this kind of approach to climate change, I asked the question, or I was asked this in a meeting, when did humans first become concerned about climate change? And about a microsecond later, I said, the Pleistocene. And this has been a human experience. This is actually my reproduction of the first Paleo IPCC meeting. And they're gathering for lunch to discuss why things are so damn cold. Our species, this is the ice core record. Our species began, at least as Homo sapiens sapien, approximately, recognizably at the glacial, last interglacial. But our whole history is in the Holocene, coming in from the last 20,000 years, and recorded history in the last few thousand years. So we're an Ice Age species, same cranial capacity back then, but completely different technologies now. But living in the interglacial, most of human recorded history, all of human recorded history is right here into the current interglacial period. And so how were authoritative statements made about the climate? The first technique was through authority, appeals to maybe it would be a philosopher, but more likely somebody who just read more than other people and wrote more than other people. And so skipping a lot of history, my climate book begins really with this fellow, Abbé Jean-Baptiste Dubois, president of the French Academy, permanent secretary, of the French Academy, sponsor of fellows into the Academy like the Baron Montesquieu, and writing about climate, but in a context of poetry and painting, critical reflections on poetry and painting, several volumes, arguing that genius is not born in every climate, but genius has to be cultivated under the proper conditions of airs, waters, soils, and your thoughts are. But early modern medicine had the thought process percolating up from our gut and through our brains, and we were very much permeated by the winds. So we had a sort of a take-home message that genius is not born in every climate, but one of the corollaries of that is it was born in my climate because I'm living in a golden age of France, of French culture. And so it's sort of like the vintage theory of genius. Like certain grapes, certain wines, certain valleys produce certain tremendous wines. Other places produce more apples and more cider than they do fine wine. And so this happens not only in geographically dispersed regions, but also in temporally different regions. So Dubois went on to talk about physical causes trumping moral causes. He gave that kind of idea to Montesquieu for sure, but also that the air, so this is an explanation of that. And he had really a geographical sense of determinism that his genius only flourished between 25 and 52 north. And if you know European geography, that's sort of like, Greece to maybe Oslo or something, or a little bit further north of there. The climate has caused these cultural ages to flourish in Greece, Rome, Renaissance Italy, and then, of course, Dubois' own time. And so he had 4 golden ages, and with the physiography of the climate system generating that. So, the challenge for the audience is to come up with the 5th golden age. Are we past it? Are we coming up on it? Are we going to claim that it's ours? I don't think we have the right to do that right now. But all these ideas, and you guys are both historians of ideas and philosophers. This percolated through Europe because there was records that the Roman inhabitation of Europe was in a colder climate than it was now. And so the theory promulgated by David Hume in his essay on the populousness of ancient nations, brought over and sort of established in the minds of Jefferson with his cold American frozen New World idea was to defend the New World. And so there's a kind of climatic patriotism brewing under Jefferson. But we were going to make it better. The American climate was cold, frozen, 40 degrees north. New York City is the same latitude as Barcelona. We don't have the oranges, et cetera. Hudson's Bay is about the same latitude as Edinburgh. And so we had to do an apologetics for the American climate. We would make it better by rolling up our sleeves, by cutting the forest, draining the marshes, taking away the kind of climatic physical threats to clear European civilization, make it more suitable for European-type, Neo-Europeans. But Jefferson he was president of the American Philosophical Society when he said this, and he said, let's take measurements, let's see what's happening. He lived in Monticello. His university was in the Piedmont, or in the front part of Virginia. And so he thought that settlement was cutting the forest and making the changes in the wind patterns. So he said, let's take data. So there's an old historiographical question about why America didn't have great theorists, but they did have large collaborative kind of Baconian data collecting activities. And Jefferson is somewhat behind some of this by having his weather diarists taking comparative measurements for all the states, repeated once or twice a century. So I think right now we do it once or twice a millisecond, but he had this idea that we should do it a couple times, like 50 years, 100 years, and watch the sea breezes march inward as the forests were cleared, watch the climate ameliorate and become a little milder as we got the marshes drained out. And there's a whole literature on this. The big question is, why did they put the U.S. White House in Foggy Bottom, right in this sort of swampy area? Maybe in 1800. With this theory, they were probably trying to kill the president because it was Miasmaville there around George Washington University. The book, I'm going to move on really quickly here because the net result of this data collection is the beginning of some theorizing about the data, some compilation of the data, some extraction of some principles from the large collections. And a fellow named James Henry Coffin, in about 1850, worked with the Smithsonian collection and came up with ideas about the wind regime. So what we know, at least in average conditions of the general circulation, was pretty well documented by laborious networks of wind measurements across Russia, across Europe, throughout the Americas. Big gaps in the data, but Coffin was able to do books like The Winds of the Northern Hemisphere, The Winds of the Globe. These are large compilations of wind patterns and maps. And then Farrell, the mathematician and sort of geophysicist, put together notions of Coriolis motion, and the general circulation was theorized by him back in the 1870s, if not before that. And so you end up with Coffin's maps of a westerly regime, surface winds, trade winds, convergence near the equator, tropical convergence, and light polar easterlies. And so you have a model, at least, of the annual general circulation, with some of the vertical sides defined by Coffin, too. He has a Hadley cell and a Farrell cell and a northern polar cell working in the vertical. And these are standard kind of maps for meteorologists. And you look at the modern version of it and you say, oh, I recognize that. And he recognized it based on these hand, I don't know how, for example, he got such vertical resolution on this, but he did. And then there's Farrell's relatively famous, reproduced lots of times, map of, again, the westerlies, the trade winds, the polar, and two hemispheres with the cells. And so we call the cell that functions mostly over our latitudes the Farrell cell now, in compliments to him. And the one in the tropics is called the Hadley cell. So we're moving on. And so there are many, many models. There were models of what was called radiant heat and how it might work in the system. And there's other people that I don't have time to include in a short lecture. But one of the models, before I get there, I couldn't help resist, and I brought it only because we're philosophers here, that models go way back. And so Democritus had solidness and shape of the atoms governing his model. I want to thank one of our chemists down the hallway from me at Colby, because he said, acids were considered to be sharp atoms that would rip against your skin or rip up your tongue, and bases were smooth things that were sort of smooth and slippery. And so the atoms must have a round shape, and this was based on Democritus' theory. The salt was sharp and pointy, air was light and whirling, and iron must have some sort of hooks. Maybe it looks like hook and eye kind of linkages that make it so solid. So when we're talking about models, and I wanted to do this purposefully, that when we talk about models, we're often going to be talking about big computers and computer intercomparisons, and the idea here is that computer/models are what's going to be the object of our epistemology. But really the model is the set of ideas, assumptions, and now equations, sometimes simplified equations or parameterizations, that go into the calculating machine called the computer. And that distinction has to be made, and I'm sure you folks do it all the time. But I wanted to say something about models and models and models that have percolated through history. Svante Arrhenius is often credited as being the first to put this together with CO2, controlling ice ages and interglacials, and his 1896 paper is really about the large geological picture. He had a geometric decline in CO2 causing a linear decrease in temperature. So he was not yet completely concerned about industrial. If you read through his paper, it's mostly about the carbon cycle linked to volcanic action and the ocean. Arvid Hogboom's model of the carbon cycle. His model's cited often, but it's really not continuous. There's a big eclipse moment that goes through most of the 20th century when Arrhenius' model was not accepted by most climatologists, meteorologists. Ekholm was his buddy, and Ekholm is a very important person who doesn't, to my knowledge, have proper biographical treatment yet. He was in Stockholm, he was with Arrhenius, and the other guy in Stockholm with both of them was Wilhelm Bjerknes. And Ekholm came up with the idea that the human influence was growing through the burning of coal, and that the CO2 growth in the atmosphere would cause a growth in the mean temperature of the atmosphere. This is 1901 paper in the QJRMS. He also speculated about regulating climate CO2 in the atmosphere, perhaps by strip mining coal seams and burning them in large amounts in case the glaciers were making a turn and coming back. So in 1901, the concern was what happens to our society if we get another ice age, and can human activities stave it off? See, it's a complete flip on what we're concerned about today. We're worried about warming. Throughout history, warming was better for most people that didn't have central heating, that lived hand to mouth in local agriculture. And so if you had cracks in your cabin, you wanted it warmer. and of course, Ekholm lived in Stockholm, but all of my storytelling recently has come through Stockholm recently, around the time about 1900. This is 1896 on Arrhenius' paper, 1898 on Wilhelm Bjerknes' circulation theory, and Ekholm standing behind all that. This is like, if there are any history graduate students or people you know that want a good topic, I think Ekholm would be wonderful, because he both was a compatriot with Arrhenius on the climate side and with Bjerknes on the dynamic side. And Ekholm did a study in which to use the technical term, he provided a perspective on what we call barotropic conditions, where the pressure lines and the temperature lines are out of phase, and they're like a sea breeze has an angle to it. And if you had a quiescent kind of situation, a baroclinic atmosphere would have everything parallel, but a barotropic would have some slope to it. And he got Bjerknes thinking about how that would make circulations in the atmosphere and how that could lead to the generation and intensification and diminution of vortexes. Because connected with Helmholtz stuff. So something was happening. I think maybe Stockholm in 1900 was another golden age for this kind of thinking to come together in the Stockholm Physical Society. And there was an eclipse of the CO2 theory. It was really out of favor. CO2 was thought to be completely washed out by water vapor absorption in the bulk method through 1950. There were some other people that brought it back, like the guy Calendar effect. So here's another fellow to look at if you haven't done so already. But he took the idea of rising temperatures in the first part of the 20th century, the idea of rising fuel consumption in the first part of the 20th century, leading up from the coal question, the rising CO2 concentrations, which he didn't have measured in a way that we do now at Mauna Loa, but he had the historical collections from the Scandinavian geoscientists showing an upward trend in CO2. And he actually guessed or gauged 190 parts per million for the 19th century background. So he came up with kind of a background number from studies of the literature, and he put together a new, very detailed understanding of infrared band absorption, particular wavelengths that were important. Arrhenius had worked with bulk absorption. Arrhenius had not had the complete understanding of the situation that Callendar was able to gather about 40 years later. And so the Callendar effect is named for the effect of the anthropogenic greenhouse warming. And it was referred to by Roger Revelle as the Callendar effect. So every time I get to say Callendar effect, it's kind of another way of naming this thing, giving credit to one of the people in the middle of the 20th century who pulled these 4 basic ideas together. He was a fuel combustion engineer. He wasn't a university scientist, never had grad students, didn't have a high status, but he worked on flamethrowers and combustion ideas in World War II for the British. In fact, he was a pacifist, so he wouldn't make flamethrowers that killed people. He made flamethrowers that lit up the airports and raised the fog by raising the temperature gradually in the British airports. And well, you're coming back from Germany, shot up, sick, injured, running out of fuel, and you can't find the British airport because of the fog. So in central England, they had a lot of planes crashing after successful bombing runs in Germany. And so Churchill allocated the petroleum warfare department's limited fuel supplies. 10% of them went to this project to light up the airports. You know, think of like the lighthouse at Alexandria. But you're flying back, and suddenly they know that the group's coming back from Germany. They light the trenches. It's like the gas burner in your gas oven. But these flames were 6 feet high. And it would cause a lighted, heated airport to appear in front of them, and then they would land. And there's even stories of them turning the burners off too early after the plane had landed, and the crew couldn't find the hangar. The frog had come back in as soon as they turned it off. So this was a brute force way of changing the weather by burning the fog off. And as soon as you turn the burners off, it would... Anyway, that's what he worked on. So he knew quite a bit. He was not able to publish about that in the classified literature, but he was able to write about the bandwidths of water vapor and CO2 as early as 1941, the detailed understanding of that. Okay, so I'm going to move on. I'll keep climate in mind as we go because we're going to come back to it. But I'm going to move on and talk a little bit about dynamics because Bjerknes was in Stockholm at the same time as these other 2 individuals, and they formed quite an influence group. Bjerknes had, I guess I would say Bjerknes was under the tutelage of his father, Carl Anton, and Carl Anton was trying to connect Maxwell's theory of electromagnetic radiation with fluid dynamics. So in about 1881, they went to in 1881, they went to the Paris Exhibition of Electricity and had a Norwegian table in which they showed that action at a distance was working through the forces transmitted through fluids. And they met people like Hertz, they met people like Thomas Edison, they met the industrialists and the thinkers. They met Helmholtz at the meeting. And actually the reports of the meeting are quite interesting, that they had quite a nice running seminar as they ran their table and they showed the forces acting through the emphasis on fluids. And in 1881, Carl Anton couldn't really go very far with the math, but his son began to take up the issue and began to put dynamics into fluid mechanics. That was his program. He worked with Hertz. He went to Poincaré's lectures. He was really quite astute at doing this. And one of his challenges was to try to get beyond the ether horizon. There was this thing called ether, which Michelson-Morley apparently had shown that it doesn't need to be assumed. It was one of those things you didn't need to explain electromagnetic propagation. And so a lot of interpretations of Bjerknes look at him as a failed physicist who left the field of basic electromagnetics and moved into meteorology because ether had collapsed as an assumption. But a new reading, I think I have a new reading of it, in which they made up their physical ether, which was the fluids of the atmosphere and oceans, and they brought the idea of Maxwell's equations onto the real fluids of the atmosphere, and then they ran into horrific difficulties of dealing with all the different nonlinear equations. So Bjerknes had the 7 equations and 7 unknowns in 1900, and he had a new ether, a kind of a real ether, I was calling it. But he left behind his, he never fully left behind his electromagnetic work, but he emphasized instead this new mathematics of real fluids. So I don't see him as a failed physicist. I see him as a geophysicist, a physicist of the atmosphere and oceans, and somebody working at a very high mathematical level of accomplishment, but with a very intractable problem. He created geophysical fluid dynamics, but then he ran up against some walls of calculation. He couldn't get the equations that were nonlinear to move forward. So really in Leipzig in 1916-17, a winter he called the Turnip Winter, in which he almost starved to death, and his associates were there in Leipzig during World War I. And he decided to move to Bergen, the second city of Norway, and take on a practical task of helping the Norwegian government provide food and fish and agriculture. He went into the Bergen practical forecasting because his, I think I have a picture of streamlines coming up. I don't know what's next. And so he was able to put together the notion that a graphical solution was the way to go forward. If you take individual observations and put them on a map, you get a wind arrow, you get a cloudiness indication in the circle, and you get maybe if you're lucky, you get temperature and pressure. But Bjerknes started to connect the dots. He started to analyze the maps and to make wind streamlines, which were swirling and whirling, a kind of an instantaneous picture of where the winds might be converging. And those streamline maps led his son, Jakob, and an associate, Halvor Solberg, to get involved in identifying them as fronts and steering lines, warm fronts and cold fronts, eventually air masses, and clashes between 2 different kinds of air that might be juxtaposed. The classic Bergen school fronts and air mass analysis came out of moving to Bergen and doing some practical stuff. Now, this slide probably could have come earlier because he was pursuing what I would call a Laplacian program, in which they wanted to have perfect measurements and perfect prevision based on the laws, equations of physics that were cast in this Maxwellian form. I would call, for simplification purposes, the maps that I was describing of streamlines were an Eulerian analysis, looking at the whole picture, like from a bird's eye view. So if you look at a map and you do an analysis of the dynamics, you're looking at the patterns. But one of the quests was to get a Lagrangian point of view, which is to follow the trajectories of take a piece of fly ash and you want to follow it through its trajectory. Or taking the bird's eye view, but following the bird instead of the view. So Eulerian was maps, Lagrangian was paths, and this was the mathematical training that Bjerknes brought, as well as a sort of a fetish for vortices. Helmholtz had seen vortices everywhere, and Bjerknes wanted to take them into the larger scale vortices of the atmosphere, eventually the general circulation. He studied with Hertz. Hertz was both Hertz died young, but he was a very proficient electrodynamicist, but also developed the first thermodynamic diagram of moist air rising and how to calculate its its potential temperature. And then the warning from Poincaré. He went to Poincaré's lectures in the late 19th century in Paris and got the clear warning that you could not measure nature precisely, and so you'd have to have you couldn't do a precise Laplacian measurement of nature. So when he did his manifesto, 1904, pretty famous, I don't know if it's famous outside of meteorology, but this 1904 paper was the clarion call for making the measurements and making the forecasts based on the laws of physics. And he had, I think Poincaré got to him, so he made he added the adjective sufficiently, a sufficiently accurate knowledge of the positions, and then a sufficiently accurate knowledge of the dynamics will give you a sufficiently useful forecast. And what they were doing in Bergen was a 2-day forecast. I call it the partial rotation of one vortex. That idea, when you watch the Weather Channel or whatever you watch for weather, they sometimes give you those little loops, and they're going like this, and you can do a pretty good job on a little single vortex over 2 days, which is what they were doing. But they couldn't get to multiple vortexes over multiple days or weeks. They couldn't do the whole dynamics and thermodynamics of the atmosphere with Bergen methods. So again, there's these taking wind measurements. There's a map that stands before this for the US, a horrible set of measurements, very loose network, 200 stations over the whole continent, over the whole continental country. And it's kind of cute the way, like Canada doesn't exist in measurements. And I was watching the weather this morning just when I first got up, and US didn't exist. I was looking for what was happening in Maine with a nor'easter, but the nor'easter came across the Maritimes, and then it was just cut off. So it was really cute. It was like appropriate, I think. But anyway, Bjerknes had mapped these things, and he'd taken individual wind arrows and connected the dots and trying to draw an instantaneous set of streamlines. And he argued that, let's say, a dirigible coming across here from the high plains couldn't go straight into Minneapolis because of the winds that would be carrying it south. So the dirigible would have to take a course which might be a longer path, but it would be a quicker path by following these streamlines. So he was also thinking about aviation at the time and connecting it to practical needs for travel. He gave 2 big public lectures in his lifetime. One was the Bergen School and how fronts and air masses work and how it's all related to geophysical fluid dynamics. His other lecture was how airplanes fly. And it was the same principle. It was a principle of vortexes under the wings and differential pressures and lifting the object. And he used to have paper airplanes that he would throw out and different kind of rotors and things that he would surprise his audience with. I didn't bring any with me today, but it was interesting to see why. So a historian comes across Bjerknes, and you're wondering, why does he have a lecture on airplanes? And when you read the lecture, you see how he's doing this double duty. One of his great acolytes, Tor Bergeron, wrote about the history of all this in his own way. He wrote it in 1959 in a volume honoring one of his friends, Carl Rossby. And he talked about the OTM idea, that observations and techniques or tools need to be prepared in advance of feeding into the models. And so we're back to models now. That was my third term. I did a little bit about dynamics, just a little bit. But models come after taking the observations. Here's the approximately 90 stations in West Norway to a very dense network, so they could do their little tiny change over space, change over time differentials. And to the west of them is the North Sea, a large body of water, uniform, more uniform in its temperature and fetch and all that. And so the storms coming off the North Sea were being intercepted by this network and then put into observational points. Some of them were visual observations of the upper air and the cloud directions. Then there were these tools of adding the streamlines, the layers of where it's raining, where it's not, where it's cloudy, where it's not, where the clouds are coming in and going out. And the whole idea was weather analysis had to precede weather forecasting. So Sverre Pedersen, again one of these disciples, wrote the classic text called Weather Analysis and Forecasting. About 70% of the book is analysis, and how to draw these isopleths and things, and then how to measure the distances between them, and then how to do the next step, which is the forecasting. Because the old weather maps were just pressure circles and temperature lines, and they had no dynamic information. What's that low pressure going to do? Well, it'll probably move from west to east. But is it going to intensify? Is it going to veer? Is it going to dissipate? There was no information in the old weather maps, even in 1920. But with this kind of thing, you had a model then that you could impose upon it, the classic Norwegian open wave cyclone, with a steering line, a squall line that we call now the warm front, the cold front. So then the path of the cyclone would be, in a way, determined by this steering line, which is the warm sector, the cold sector over here. And then they developed even a family of these things, the idea that they come in fours, or sometimes they come in fours. They would like to have an ideal model where they all came in fours, but sometimes they came in twos or threes. And you have the idea of an open cyclone. The cold front catches the warm front. This becomes the seclusion. This becomes the occlusion. And occlusion comes, in our current English, it comes from dentistry. So the bite, the occlusion of your front and lower teeth. And that's when the cold front catches the warm front, lifts all the warm air up, and the rising air cools, and the cooling air condenses, and the condensing air forms precipitation. So there's a family. They were expecting to have at least four vortices in a row, maybe over the course of a week, that would come off of the so-called polar front. Bergeron wrote about dynamic climatology in 1930, just about 12 years into the Bergen school. And he said, let's take this idea of air masses and fronts and universalize it, look at it in a long-term situation. And so we end up, I can't speak so much for London, Ontario, Canada, but I can speak for Maine, in which we have three air masses that are always competing, the continental polar and the maritime polar and the maritime tropical. And where three air masses meet, it's like Mark Twain said, you don't like the weather, just wait a couple minutes, it's going to change. So we have these competing changes, which helps to form our climatology of a very variable, even daily, weekly climate change. And so there's a lot of literature that, and in fact, it's almost a perennial literature of the 20th century that looks down on descriptive climatology for offering no unifying picture of the thermodynamic forces. And his program was to apply the air masses and fronts to a dynamic climatology that showed how the elements would be organically and dynamically interrelated, to try to get to, I think, what you call climate dynamics now. Climate dynamics needs to have its vortices, it needs to have its air masses considered in its modeling. And the classical, I don't think this has been written either, so it's another good project to write the history of a couple different threads of climatology. One more traditional, based on plant geography, kind of a Humboldtian correlation between plants and climates, more descriptive, and another being more theoretical with the climate modelers and the feedback that goes into the model. Local, global. Of course, we did a special issue of Osiris maybe 3 years ago, in which we argued that climate was always something much bigger than average weather or weather statistics. It was the fabric of our lives. It might be cotton for sure, but the fabric of our life was the kind of regions we lived in, the kind of expectations we had, the kind of, in a way, foods and seasons that we would expect in a clima kind of local incarnation of climate. There's a little bit, there's what I meant about, well, maybe it is true here too. I guess London, Ontario, Canada's right about there, right? So we're not that far away, and you have three air masses that probably compete with you. We don't get the warm air from the south too often where we live. This is the summer pattern. This is the winter pattern dominated by the westerlies, and the polar front would be across here. So Bergeron was working on this. So that's something about models. But I also mentioned earlier in the talk that the period I was interested in now went from Marconi Wireless to Tyro Satellite. It went from the Wright Flyer to aerospace. And it punctuated in the middle was this thing called the bomb and outdoor nuclear testing. And all these technologies, none of these technologies were invented by the meteorologists, but all of them were quickly appropriated. So within 2 years of Marconi spanning the Atlantic, the Weather Bureau had hired R.G. Fessenden to work on wireless communication in the weather services. Within a few years of the Wright Flyer, they had weather services in the military. Made a very big difference in the way that aviation was considered in relationship to the weather. So technology plays a role in this. It played more of an enabling role, an inspiring role, and just in a way, kind of an aside here, a lot of the literature about meteorology in the 20th century is written about the weather services, the weather bureaus, the bureaucratic history. It's extremely deadly. It's extremely declensionist, I'd say, that we don't have the funds, we don't have the vision, we don't have the ability to do what we want to do. And so I call it if meteorology is my 100-acre woods, I call this the Eeyore version of history. Oh, we can't get it done, we can't do that. And my researchers were the Christopher Robins. The Bjerknes was always excited. He got involved he knew from Hertz, he knew exactly how wireless worked. He was involved in the installation of a wireless station in Norway. And he was very excited to adopt and adapt and appropriate, if you would, these new technologies into his work. And wireless is one of the ancestors of radio. The radio tube is one of the technologies used in the ENIAC. And so there's a continuous electromagnetic history that leads from Marconi through computing. And there's a continuous history, of course punctuated, but from aviation to aerospace with the launching of the rockets. Again, a lot of histories of the 20th century in atmospheric talk about one technology, the rise of digital computers, the greatness of the holy land that we finally got to, the promised land of digital. But there's so many technologies. There was radar, there was radio sondes. And I know, I don't know what your group is totally like, but how many people have written a philosophy of radio sondes? Or Roman, you're doing philosophies of things, right? So I'm just kidding you. We had an early discussion about the word of. But if you look at a radio sonde, it's the ancestor of remote sensing. You're getting information from a remote location. Before you had to have a tethered kite, a tethered balloon, or no information, or just observations of clouds passing over. But with a radio, you get remote sensing, which becomes the technique for getting information from the space age through radio. So just 2 weeks ago, we went to Asbury Park, New Jersey. We saw the big Tyros dish that's still there. I mean, it's a signal office, signal core dish on the coast. And it was the antenna that allowed the Tyros first satellite pictures to come down and then were helicoptered down to Washington to give to President Eisenhower at the time. It was a really big deal to think about this era. And I decided to cut it off about 1960 when my key protagonist left the scene. And when this more bureaucratic field of atmospheric science run by committees began to emerge in the period after the International Geophysical Year. So Marconi captured V2s. The space age did not begin in 1957. The satellite age began with Sputnik. But the space age, we were already at near space and the edge of space and taking photographs from space in 1946. These were military rockets, but they were adapted and adopted immediately to put a second stage on and get them up into the atmosphere with cameras and sensors. Then the bomb is a third technology beyond aerospace and communications. The bomb, again, was immediately appropriated for its nuclear tracers and for the ability to see and follow radioactively the trajectories of particles. And Gavin has a question.
So the V2 rocket, the first one that took a picture from space, was actually launched today in 1946.
Here we go. Let's raise it. Raise the glass to the air. I think it was an airplane pilot, please. You have internet back there? You have your Wi-Fi running?
I do have it.
Okay. And then the computing, the ENIAC that ran some of these equations. There's much more to say. I think I'm running short on time. I'm supposed to leave time for discussion. And I'm not going to go into Landsberg, but a sufficiently accurate forecast for these people was a partial rotation of a single vortex throughout the 20th century. And the idea of calculating the weather is kind of a little bit of a misleading phrase because in 1950, they didn't calculate the weather, but they calculated a friction-free ideal flow at 500 millibars. And so one of the guys I didn't have time to talk about was Bjerknes' disciple Rossby, who took the horrific set of complicated 7 equations, nonlinear, brought them from the surface to a halfway point in the atmosphere, and said, well, let's make the approximation that at this level we can make an artificial plane, called it a beta plane, but something like a flat plane across a nation, and you could think of the friction-free flow at that level. One of my professors was always writing equations all the way across the board, and then he'd start erasing them from the right side. He'd say, well, there's no friction there, and there's no diurnal heating there, and there's no water vapor there. And now we can solve this part of it and get a Rossby wave kind of equation out of it. Of course, he worked in spherical coordinates, which made it more hard. But on flat coordinates, it was pretty clear that this is what they were putting into the early models to try to connect the upper atmosphere with the lower. Then they did the infinite forecast. Norm Phillips ran the computer model for a long time and generated some of the statistical features of the general circulation in 1955. And then it's not yet possible to do multiple rotations of multiple vortices. You can emulate that. You cannot do a perfect long-range forecast, which is what the planners want. And then perhaps for discussion is the idea of the perturbed climate system. When you start adding more than dynamics and thermodynamics, you start adding industry and even geoengineering into your models, then you're adding all sorts of nonlinearities and all sorts of parameterizations that may not make it possible to do a prediction of the future state. And the Gordian knot that was mentioned in some of the conference literature, but I think technology helped to cut through the knot, but we still have the knot to think about philosophically. What would you like to do? Would you like to discuss stuff right now? Or I'll give it a little tagline.
We have 12 minutes. We've taken another couple minutes.
I wanted to get back to the brick wall before I ended, because I promised you a brick wall. And the warning about the wall coming up was from Poincaré about 1900. The actual wall came in Tokyo in 1960 when Ed Lorenz gave a talk to the numerical weather prediction group. Charney was there, Bert Bolin was there, everybody who was anybody and still alive was there in Tokyo. That's what historians speaking. My guys were good, but they were dead by then. 2 qualifications to be in history. But Ed Lorenz he gave a talk about how his model was producing a simple 3-equation model climate was producing forecasts, and the forecasts were degrading after 5 days. And after about 2 weeks, they were unrecognizable to the initial conditions. And then he just ended up with this notion, and he didn't publish it till 62, but he spoke about it in 1960, that the statistical properties were, or his definition of climate, the set of statistical properties and its surroundings that could exist at a time not too distant, given the present state, plus some uncertainty, and assuming no change in external influences. This is his definition of climate. I was recently, he passed away in recent years, 2006 was it, or 8? His papers are at the Library of Congress now, and I was in there before their accession. I was working in the cardboard boxes. And every one of his lectures is prepared in packets, in manila folders as transparencies, and his hard drive is in there. And so there's a wonderful chance here to do kind of a study of Lorenz's influence on this field, because it was really dramatic, a beginning of an end to the Laplacian program. And he talked about climate having one or more attractors. So the precise prediction of climate, I think you guys already know this stuff, but he talked about the climate of the model, and he was able to, in the last part of his life, he was up at Colby, we gave him an honorary degree. He was lecturing on regime change in a climate model, using 3 simple equations again, and showing how he could get a kind of a paleoclimatic jumpiness out of his 3 simple equations. Very much a mathematician thinking in parallel with the kind of thinking that Rossby did to simplify things, but then showing that simplification brought a new complexity to it. And so he's writing about regimes in a simple system at the end of his life, and when one behavior persists for a long time, then switches, and then switches back. And there's kind of this jumping between branches of the strange attractor. And I'll just end with his handwriting. This is drawn out of the Library of Congress collections now, but it was a transparency that said, sorry, this is about weather, but you learn to make a essentially perfect weather forecast. That would be the Laplacian program. And then you make the best possible forecast, even far from perfect. That might be the Bergen approximation. And then you have to learn how good the best attainable forecasts are, even if we don't learn how to make them, which is this is probably true in about the 1960s and maybe continuing. And then why should nearly perfect forecasts be unattainable? And his punchline for his talk was chaos. So I wanted to give you a picture of climate really from the Pleistocene where we started. I mean, the big picture, the climate is a shape-shifting noun. And when you say climate and you're being a philosopher in 1900, you're talking about something different than today. And also dynamics, which is this evolving thing that came out of some of Maxwell's dynamical theories applied to fluids. And then the idea of models, which are the conceptual package that goes into a calculator, a computational routine. And then the idea, then the fourth idea is that of the brick wall, probably set up by Poincaré, but brought home by Lorentz. And I was at the 50th anniversary of numerical weather prediction, and there's really are two schools. Give me a bigger computer, and I'll crunch it out, and I'll do ensemble work, and I'll bring you, maybe the best possible, not necessarily the perfect forecast. And then there's the Lorentz school, which was saying, but, just basic saying, but. So I'll leave it at that, and we'll have some time to discussion. Thanks you for your attention. Thanks for the attention.
Very much. Question?
I love the notion of culture being environmentally determined, and moreover trying to create golden ages by changing the environment. The Jefferson quote where he says the effect of clearing a culture towards changes of climate, that sort of suggests to me that it's the relationship is sort of bidirectional, right? It sounds a bit like, so I'm asking whether this sort of 18th, 19th century environmental determinism, is that just in one direction, or can the Jefferson quote sort of suggested to me that actually by shoving a bunch of people with a certain culture in an area, right? Mm-hmm. So if I have a bunch of immigrants going over, they might themselves also change the environment, and so it's kind of two-directional. Is that the sort of picture?
Not only would they possibly change the environment, but they would change the discussions about it, which is somewhat equivalent to changing it. Climatic change could be seen in the Enlightenment as the threat of moving to another climate. The best life for Debaut was lived in a French wine-producing, bread-producing valley. And if you wanted a perfect life, you would stay near home and have all the culture somewhere near Paris, probably. But moving to another country, moving to another climate would put you in contact with the airs, waters, and places and aboriginals of another place. So that was climate change, as well as what we'd call today global climate change. This was personal climate change. And so the discourse could change as you move. Climatic determinism, you think of it as something that's way back there. That was something back when they didn't know any better. But you have climatic determinism in the 20th century connected with eugenics and Ellsworth Huntington's work. You have climatic determinism lasting, the geographers claim the dragon was finally slayed in the 1950s or something when we got away from all that kind of stuff. But I think if you looked at contemporary literature, not necessarily all the science, but climate is a topic that's written about by many, many people, some of them that don't know very much about climate, but they know about other things. And if you look at that literature, a lot of it has these deterministic tropes in it, that we are facing an inevitable this or that there's and it's just like environmental determinism, technological determinism, climatic determinism have an inevitability statement attached to them. And I think you'll find it in contemporary literature about Canadians going to the tropics are going to be enervated by the vast of heat. You find this in our U.S. State Department warnings. Or you find it in the developing world will simply not be able to get their thing together, so the developed world has to help them. And you get these kind of statements that are subtly embedded in a lot of the UN literature about climate change. So I think climatic determinism continues to rear its ugly head almost like a perennial philosophy. I don't know if that helps. That's what I think. I'll go with you.
Just following up from that, I mean, so, there was this horribly culturally biased climatic determinism that was a very kind of 19th century idea, kind of persisted well into the 20th century. But we have a lot of evidence now that changes in climate do actually impact civilizations and are possibly responsible for various city-state collapses in the Mayan cities or in Angkor Wat or something like that. But those kinds of ideas, even when you have actually quite good paleo records demonstrating that just before the collapse there was a multi-year period of extreme drought, a lot of historians feel like that they have to push against that because they're trying to avoid the sins of their fathers. Yet, it's not inconceivable that climate extremes and climate changes do impact civilizations' ability to feed themselves and to sustain populations in very distressed situations.
Okay. Is that a question? No. It reminds me of the 1939 World's Fair where Ellsworth Huntington was involved with some others in a conference called Biophysics, Biocosmics, and Biocracy. And biophysics will tell you that a human organism can't live above whatever it would be. Let's say 105 Fahrenheit and down below 90 or something. Your core body temperature limits. So there were some biophysical results coming out in the 30s. And then biocosmics was this idea that climate and civilization were broadly correlated across the globe, that the high cultures came from somewhere. Huntington lived halfway between, or commuted between New Haven and Cambridge, Mass. And that's where the best climate in the world was for thinking. Because that's where the storm track was, and that's where inspiration came through regularly every week or so. He used to throw the windows open and write a paper during the passage of a cold front. And also high civilization could be found in places like Northern Europe and Southern Africa and, Mediterranean, Australia, but very, very few other places. And he did this by taking surveys of people. So there is truth to these statements, but and then the what was it called? Biocosmics, biocracy. Biocracy was something like we'd call today biopolitics, or some wisdom of the body applied to the world. And these were large intellectual excesses. I'm not going to call them errors, but there's a grain of truth in all of these things. And there's a lot of geographers now writing about resilience, robustness of civilizations, not trying to put everything into the climatic basket as an explanatory technique, but looking at why did certain things happen. Maybe it's a very complicated complex of, usually it's disease, climate, and something else that goes together. And untangling all those things is really the task. I think historians got burned a little bit by Jared Diamond and the strong determinism of collapse and all that kind of popular literature. But I don't think we're just simply reacting to that. We're trying to get particular details out of it. And you had your...
So I'm Vanessa Schweitzer from the University of Waterloo.
Cool.
And my question for you was to get kind of your historian's perspective on how you pointed out that there was this eclipse over recognizing the importance of carbon dioxide as a greenhouse gas,
Right.
what sort of climatic effects it can have. So to the extent that now you have people who are skeptical of this particular hypothesis, would you say that those people are kind of conveniently trying to resuscitate like a dead alternative, in terms of trying to argue against it?
There is that's a possibility, and some of them might, but I'm not sure about that. The historical eclipse came when people jumped on the Arrhenius bandwagon, then other people had pointed out some thermodynamic realities of the time. And the story of the 20th century has been the increasing wavelength and and resolution of the infrared. So you can think of it through an infrared history that Arrhenius only had bulk infrared out to about 6 microns, didn't have the water vapor overlap or anything like that. And so other physicists said, well, this is not possible, this is not working. I did have to face a point, when I was writing the climate book, I had to face a point where could some of this stuff I'm writing be used against the mainstream of climatology? And so I had to deal with, could this history sort of be X-rated, and should I be worried about that? And possibly in some cases it has been misused or harvested for things like that. But the eclipse was more of a theoretical move to say the theory was not overthrown, but it was kind of like yesterday's eclipse. It was either a partial or total eclipse, but then it passed by, like a cloud over the sun, but came back around as calendar began to put the details back together. So theories can go out of favor, and they can go out of favor for good reasons, but sometimes some of the more perennial ones come back, and I think this human influence thing is a perennial thing. Because people said, wow, look, humans are influencing the climate, and I said, yeah, they were thinking that way back in Jefferson's time too, but for different reasons, the theories come and go.
Well, let's take one
One
more
more?
question before. Wendy, do you have one?
Mine's pretty detailed, so it's a narrow question, so if someone else has a.
Did you call it cat to go to the airport?
Okay.
Go ahead.
I was intrigued by this, number 3 on Lorenz's list here, learning how good the best attainable forecasts are, even if we don't know how to learn how to make them. And you kind of think, well, how are you going to learn how good they could be if you don't know how to make them? And you might, to me, I thought, well, maybe he's talking about looking at how rapidly nearby initial conditions diverge, and
Right.
where he came up with that estimate that 2 weeks is something like the theoretical limit on what we can hope to forecast. But I was just wondering if you knew whether in any of his if you had any other ideas on how to think about learning the limits of what the best attainable forecasts are, besides looking at how quickly nearby trajectories and simplified, not perfect models diverge, which might be a clue, but you wouldn't necessarily have to say that's actually showing us the theoretical upper limit.
Yeah, I'm suspecting, and this is going to be a future research project in greater detail, but expecting what I know about Ed, and in some cases from Ed, I asked him once, he doesn't really, he never coined the term butterfly effect. You know this story. He's thinking of seagulls out in the sea breeze over Cambridge, Boston, and there's a lot of stories I could tell about this, but the basic thing I said was, could a perturbation really change the climate? And his response was, perhaps if it's as big as the Rocky Mountains, not sort of like the Mothra effect rather than the butterfly effect. And Smagorinsky had said this too. He said, if you take, and a very famous case study done by climatologists of putting in the Himalayas, taking them out of the model, showing the difference it makes for Africa, that kind of sensitivity. So yes, there's sensitivity. Then there's the other approach, which says that every model run is not the same as every other model run. And this goes back to Bergen forecasting. When Pedersen, the fellow that did weather analysis and forecasting, had to do the Anzio invasion forecast, there was a big high pressure sitting over Italy. And he had to give a 7-day forecast. He says, no problem. It's going to be nice for a long time, as long as this high pressure sets up. So there are situations that he could forecast way out beyond what might be called a theoretical limit. But when he had to do the D-Day forecast for the stormy English Channel, it was very dicey and everything was changing very quickly. And so I guess if you had different kinds of electronic models in those days running, they would put out different kind of spaghetti plots, and one would be very divergent, one would be very convergent. And so that might be one way that people are trying. And I did portray 2 camps, but I think there's a lot of work between big computers and chaos theory, trying to think of ways to work across the boundary. So I don't know. It's a future research project. Maybe it's something you thought about too.
Well, he always has such creative ideas and thought, just an amazing scientist, and I didn't know if he had any other ideas beyond the sort of looking at the sort of average rate at which
Right.
Nearby initial conditions diverge. But
I think if you looked at his jagged paleo chart in the earlier slide, he would say that some rates are very fast and some rates are very slow. Some environmental changes, even without humans, were very fast. We had incredible environmental change in Maine when the glaciers were deglaciating and the crust was rebounding and the ocean was sliding back to the Atlantic. That's how we got landlocked salmon. And there was no human involvement in that at all. And then there's other periods where things are very quite well behaved on the attractor. And so I guess one of the interesting research questions is getting into the big computers and chaos camps and seeing how they're moving across other boundaries.
Afraid we have to stop and have a coffee break.
I'm happy to stop. Thank you.
Thank you very much. And so we'll take 10 minutes for coffee break, not more, please. Help yourselves to the nice stuff out there. If you didn't already notice, there's the Wi-Fi network. Let's thank Jim again.
Thank you. Thank you. Very good idea.
Thank you very much.
Oh, I appreciate it.